In computer networks, we are taking chapter number 2, that is the physical layer. The maximum data rate of a channel. So in any channel, wherever the communication is taking place, so there is a limit, okay? That is the data rate or bit per second, how much it can send or allow. So 1924, an AT&T engineer, he is Harry Nyquist. He realized that even a channel which is regarded as perfect, that also has a finite transmission capacity, bit per second or sending rate. So Nyquist, he derived an equation, and he derived it for the noiseless channel. So he derived an equation and expressing the maximum data rate bit per second for a finite bandwidth, especially in noiseless channel. In 1948, Claude Shannon, now he carried forward Nyquist's work and extended it to the case where the channel has noise. For example, random noise, thermodynamic noise, thermal noise. Okay? Nyquist, noiseless channel, Shannon, noise channel or noised thermodynamic thermal channel. So Nyquist proved that if an arbitrary signal, any signal, through a low pass filter of bandwidth B, so the bandwidth is decided, this is the bandwidth, capital B. So this can be completely reconstructed by making only 2B exact samples per second. That is, one computer sending to another. We need, according to Nyquist, the signal can be reconstructed by making only and only, that is the exact 2B samples per second. So sampling the line faster than 2B, what does it mean? It is pointless. Why we are not talking about this? Because the higher frequency component that this kind of sampling could recover has already been filtered out. We have already used the filter. So the Nyquist theorem states that for signal of V discrete levels, what is this V? Now the Shannon doesn't have this V discrete levels. So Nyquist theorem, I'll just tell you about the levels. So the maximum data rate will be 2 multiplied by B bandwidth multiplied by log base is 2 of V. V is the discrete levels. So this is the maximum data rate. I'll give you an example of that. So because Nyquist talked about noiseless channels, so let us consider we have a 3 kilohertz channel. Now these 3 kilohertz is the bandwidth, 3 kilohertz, and this channel cannot transmit binary. What is the maximum data rate? Binary means 0, 1. So we are talking about 2 levels. So this capital V is this level, this discrete level. Here for binary we are using 2. So this 3 kilohertz with 2 level, the maximum data rate is only 6 kbps or 6000 bps, bit per second. When it comes to noisy channel, we also call it as Shannon capacity. See, take any object, take anything, there will always be some random noise, thermal noise, because there will be molecules will be in motion, and there will be some motion producing heat, very minute, but still it will be there. So there will be a thermal noise, thermodynamic noise. And this thermal noise is measured by the ratio of signal power, let us say S, to the noise power, capital N. That is, the noise is computed as signal to noise ratio, the signal power being sent and the noise present, noise power. So signal to noise, we also call it as SNR, signal to noise ratio, S by N. So this ratio can be very large. It can go up to a very high number. So in order for the computation to take place mathematically, we would like to make it in a range so that we can handle it. That is why this kind of ratio, in mostly other examples also you will see, this will be expressed on a log scale. So 10, then log, base is also 10, and then we have S by N. As I said, we are trying to mitigate the tremendous range. So the units of this log scale, we call it as decibels. dB. Deci means 10 here. And what is bell? Bell is for the honor of Alexander Graham Bell, who first patented the telephone system. For example, the signal to noise ratio of 10 is 10 dB. The ratio of S by N, 100, is 20 dB. The ratio of this S by N, 1000, will be 30 dB. So this will be easier to compute also and to understand also. So this is the decibel. We are converting it into a decibel or log scale. So Shannon capacity or Shannon's major result is the maximum data rate or the maximum capacity for a noisy channel. Okay, Nyquist, noiseless channel. Claude Shannon, noisy channel. So he said, or he gave the expression, maximum data rate will be bandwidth multiplied by log, the base will be 2, 1 plus S by N. S by N is signal to noise ratio, bits per second. So B, you will always take in hertz. If it is in kilohertz, you have to convert it into hertz. And the signal to noise ratio, S by N. This is the maximum data rate. Let us take a real life scenario here. We know the maximum data rate of Claude Shannon. So it depends on what? Bandwidth and signal to noise ratio. So you have in your home normally ADSL, asymmetric digital subscriber line. So this is providing the internet access over the normal telephone lines, and this uses a bandwidth of 1 megahertz. If you take 1 to 2 kilometer short lines, the SNR or signal to noise ratio of 40 dB is quite good for reception. Now it is mentioned that channel can never transmit more than 13 Mbps because we have the maximum data rate capacity. You will see that these ADSL will have a number written, 12 Mbps per se. So in order to improve, either we have to improve the bandwidth or signal to noise ratio. In order to improve the SNR, signal to noise ratio, we can put certain digital repeaters. Repeaters enhances the energy, boosts the energy, the signal strength. Or we can use more bandwidth, as we have been doing with a new evolution of this ASDL, that is ADSL, that is the ASDL2+. Okay. Digital modulation. See, we are dealing with wires or wireless channels. Now these channels, they carry analog signals. Okay, this can be done using voltage, light intensity, sound intensity, so we can vary it, and then these wires and wireless channels, they can carry the analog signal. So if you want to send the signals on this analog channel. For example, you have bits. You have to send it on wire. So how to send these bits on the wire? Wire will have, because this is an electrical component, it will have a voltage, it can have a ampere. If fiber is there, it can be light. Okay. So the only idea is to vary all these, and with different voltage, different bits can be sent. So to send a digital information, that is 0, 1, 1, 0, like this kind of thing, this kind of binary digits or bits, in order to send this digital information, we must devise analog signals. Those can represent these bits. For example, we have multiple computers. One computer is sending, say, 1011, and the other also has to get 1011. But the channel or the mode are analog. So how to represent this 1011 in terms of sending, so that the wire can take this 1011 and the other computer can understand that 1011 has come. So this exact process, the process of converting between these bits and signals, is called digital modulation. Okay? Let me tell you again. The process of converting the bits, digital bits, binary digits into signals is called digital modulation. So there are various schemes. There are various schemes that converts these bits into signal. And these are called baseband transmission. Baseband transmission. I told you about baseband signals. So the schemes that converts bits into signal, baseband transmission. And what is the basic thing? The signal here will occupy frequencies from 0 to certain maximum signaling rate. Let us write it as max. This is the baseband signal. Very common to the wires, coaxial cable, twisted pair. Very common baseband transmission for the wires. But there are certain schemes, rather than voltage intensity or sound, light or sound, it can regulate the amplitude, phase and frequency. See, any signal, it will have some amplitude like this. It will have some angle, that is the phase, and number of oscillation, that is the frequency. So there are certain schemes that can regulate, that can modulate, that can change the amplitude, phase and frequency of a carrier signal to convey bits. And these are called passband transmission. What are these called? Passband transmission. You understood the difference between baseband transmission and passband transmission? Okay. So these are the schemes where we are changing, varying the amplitude, phase and frequency of the carrier signal in order to represent the bit. In this passband or band pass transmission, the signal will occupy a band of frequency around a central frequency, around the frequency, and this frequency will be of the carrier signal. Right? This is the central frequency I am talking about, passband transmission. And this is very common for the wireless and the optical channels, where the signals has to reside in a given frequency band. There is a particular frequency band and the signals have to reside inside this. There is one more concept, multiplexing. Now there are multiple people who want to use this channel or the road, say. When all these three can go together, so the channels or the road, those share or they are shared by multiple signals. Here we are taking the analogy of people. So channels are shared by multiple signals. This is called multiplexing. In baseband transmission, there are different schemes. The best way or the easiest way, we are talking about voltage. Whenever you touch a wire, you will feel some current. That is, you have some voltage, some current. So the most straightforward form of digital modulation, that is from bits to signals, is simply to say positive voltage as 1 bit or a negative voltage as a 0 bit. Okay, we can represent a positive voltage by 1 bit and a negative voltage by a 0 bit. This is the most easiest way. But when you talk about the optical fiber, how do we change it? How do we decipher it? You can say that the presence of light can be regarded as 1 and the absence of light can be regarded as a 0. So this scheme is nothing but NRZ, or non-return to 0. The scheme is called non-return to 0. Okay, so let me just give you idea here. 1 is for high signal, 0 is for low signal. So this is the whole bit 0 0 1 0 1 0 1 1 0. We are saying wherever 1 is there, we are saying high signal. So let us see all the ones and just put a high there. That is 1 here. Wherever 1 is there, 1 here, 1 here. So I am just putting a line wherever 1 is there. And wherever there is a low signal, that is 0. This is 0. This is also 0. And just combine this. This is non-return to 0 or NRZ. 1 high signal, 0 low signal. Now the problem, because every scheme has some downside, because we are discussing about not only the sender, the receiver also has to receive. Same bit sequence has to be received. So how about sending lot of zeros, lot of ones? This problem persists. So it is difficult to interpret zeros and ones, which is called as a baseline wander. Okay, so receiver, what it does? It converts this into bits because it has to sample the signal at regular intervals of time. You can say clock. So at every, say, regular interval of time, at every clock pulse, it will try to retrieve through sampling the signal. Whenever you send the signal will look different because in between it will lose energy, it will be attenuated, distorted by the channel. So you may get some noise at receiver. So in order to decode the bits at the receiver end, the receiver need to map signal samples to the closest possible. If some 4 volt is there, it will say, oh, it may be 1. Okay. So for this NRZ, a positive voltage will be taken as 1 and the negative voltage will be taken as if 0 has been sent by the sender. But this NRZ is seldom used, is not much used. Therefore, we have, considering the different engineering consideration, wire, technologies, all these signs, line codes are there. These are different line codes that better meet these engineering considerations. With this NRZ, non-return to 0, the signal, it may cycle between the positive and the negative levels up to every 2 bits. Just take a case of alternating ones and zeros, 0 1 0 1 like this. So the signal will cycle between the positive and negative levels up to every 2 bits, right? Now this means what? We need a bandwidth of at least B by 2 Hertz. We need that. What does it mean? When the bit rate is B bit per second, we need at least B by 2 Hertz. So we cannot run this NRZ faster if we don't have extra bandwidth. So without using additional bandwidth, we cannot use it because I showed you the scenario. But the bandwidth is limited. Even for the wired channels, the bandwidth is not that much freely available. If you want to send the high frequency signal, what will happen? High frequency signals are susceptible to attenuation for the loss. And even we would require faster electronics for sending the high frequency signals. So there are certain scenarios to be thought here also. So what is the strategy? The strategy is we can use more than 2 signaling levels. This we can do. We can use 2 signaling levels. So before we talk about this, by using I'll talk about the bitrate and baud rate. So by using the 4 voltages, for example, we are using 4 voltage now, we can send 2 bits at once as a single symbol. That is, these are the combination. So here we have, these are different voltages, and for every voltage, 2 bits we are sending, and we are calling that we are sending 2 bits at once as a single symbol. 00 is not 1, it is a single symbol. 11 was 01, 10, these are one symbol. So the rates at which the signal changes is half the bit rate. Okay? Because we are using 2 now. So needed bandwidth has been reduced. So rate at which the signal changes is called the symbol rate. Rate at which the signal will change will be symbol rate, and that is called as a baud rate. Baud rate. So signal changing rate is baud rate. And what is the bit rate? Bit rate, I'll just tell you, I'll give you the difference also. So bit rate is computed how? We have to multiply the baud rate with the bits per symbol. For example, here we have 2 bits per symbol. Okay? And one thing you need to note, that the number of signal levels, they does not need to be a power of 2. Bit rate and baud rate. Bit rate is the number of bits that are transferred between devices in 1 second. We call it as bit rate. You can also call it as the speed. This is the rate at which the data is sent. 1 second, how many bits are sent? The unit is bit per second. You can also call it as a measurement of speed, bit rate. And baud rate is the number of times a signal in a communication channel changes its state. Okay? The changing state of signal is baud rate, and the number of bits that are transferred in 1 second is bit rate. So the signal number of time it is changing its state is baud rate. I'll give an example. Okay, see here, we have 0, 0, 0. These are 3 bits. That is, the number of bits per signal is 3. Number of bits per signal, you see 001, 000, all these are, they are number of bits per signal. They are 3. I am saying that the signal changes, say, 20 times per second here. So the 20 is the baud rate. Signal is changing 20 times per second, that is the baud rate. And the number of bits per signal is 3. So how do we get the bit rate? The bit rate will be the number of time the signal changes, that is the 20, multiplied by the number of bits per signal, which is 3 here in this example. 60 will be the bit rate, that is the bit per second, for the baud rate of 20. So here you see 2 more figure. So this has a baud rate of 1 baud, and a bit rate of 1 bit per second, only 1 bit is going, 1 bit per signal. Here you have 2 bit per means you have in a one symbol 2 bits. So baud rate still is 1 baud, but the bit rate is 2 bps. One more example. Here you have 3 bits. I have given a line here and there are combination of 3 bits. So the bit rate will be simply 3 into n. N is what? The baud rate. Similarly, if you have chord bit, 4 bits, and baud rate remaining n, the bit rate will be 4 into n. So the schemes we have discussed, all the schemes that encode the bit into symbols or the signals, receiver has to know when one symbol is starting and other is ending, so that the next symbol begins to correctly decode the bits. This is the responsibility of the receiver. If you have long series of zeros, how can a receiver tell? It will be difficult to tell the bits apart because there are a number of zeros. So the only thought is we can have an accurate clock like we have in GPS, the atomic clock. Then it can easily tell where the symbol is ending. But it is very expensive. So the strategy would be, we can send this clock signal using a different channel. That is, we can send a separate clock signal to the receiver. One will be for data, one will be for the clock signal. So now the sender will know, sender and receiver will have same clock. It can easily find out where the symbol is starting, where the symbol is ending. But the problem is, if you are using another clock, why not to use it for the data? Why are you using single channel for sending only the clock signal? We can even use it for sending data. So the idea is, a clever idea is, we can mix the clock signal with the data signal, because the clock can only be used to find out where the data is there. So we can mix the clock signal with the data signal by using XOR. We will not need any extra line, which we were just discussing to send the clock signal. So the clock will make the clock makes a clock transition in every bit time. So it will run at twice the bit rate, because the clock is making a clock transition in every bit time. And since we have XORed the clock signal with the data signal, XOR you can see on the right, I have shown you the truth table. So when it is XORed with a 0 level, when we have 0 0, it will give you 1. When you have 1 1, it will give you 1. If they are different, 0 1 1 0, you will get a 0. So when XORed with a 0 level, it makes a low to high transition. That is simply the clock. Okay. So the transition can be termed as a logical 0. When it is XORed with a 1 level, it will be inverted. And now it will make a high to low transition. So the transition is a logical 1. Logical 1 here. What I am trying to suggest here is that whenever you see a 0, it will be like this. Whenever it will be 1, it will be like this. The whole story is this. So you see here, whenever we have 0, it is going like this. Whenever we have 1, it is going like this. Take anywhere. 1. So it is going like this. Again we have 1, then we have 0, so it is going down. So this scheme is called Manchester encoding. This scheme is called as Manchester encoding, and this was used for classic Ethernet. But what is the downside of the Manchester coding? As I said, it requires twice bandwidth as the NRZ because it has a clock also, and we were XORing it also. So there can be different strategy thoughts. We should code data to ensure that there are enough transition in the signal. We can code the data itself. That is, coding a 1 as a transition and a 0 when there is no transition, or vice versa. So this kind of coding is called NRZI, or non-return to zero inverted. Non-return to zero inverted. Here is an example. What you have to do is, wherever you see a transition from 0 to 1 or 1 is there, make a transition. Wherever it is 0, just make a straight line. Now you get a 1, translate it. Make a transition. Again 1, make a transition. 0, keep it straight. Again 1, make a transition. This is called NRZI. In Universal Serial Bus USB, this standard for connecting computer peripherals, they use NRZI. Now, in order to fix this long runs of zeros, what we can do? We have multiple solutions. We can divide or break up these long runs of zeros. It can be 50, 40, 20 zeros. So we can divide this, say 20 zeros into 5 zeros or 4 zeros. This can be a solution. So the strategy of this, there is a well-known code to do this, is 4B and 5B, oblique 5B. What does it do? The 4-bit, every 4-bit is mapped to a 5-bit pattern, and there will be a fixed transition table. 4-bit is 2 to the power 4, so 16 combination. 5-bit is 2 to the power 5, that is 32 combination of zeros 1. So now we are mapping the 4-bit to 5-bit, and there will be a fixed transition table that you see here also. That is 0, 0, 0, 0, 4 zeros will be having code word as 1, 1, 1, 1, 0. Okay. This is 4B, 5B table, transition table. What you will get, what is the benefit? You will never have more than 3 consecutive zeros. Say you take these 2 zeros. In the end, you will have maximum 2 zeros, and in the front you will have 1 0. So if you combine this end and front, there will be maximum 3 zeros. These 2 zeros and this 1 0. Any combination you can take. So there will never be a run of more than 3 consecutive zeros. So this is how we fix the long runs of zeros problem. But this kind of 4B, 5B screen, because there is a transition table, there will be a 25% overhead, but it is 100% better than, means the Manchester encoding is having 100% overhead. One more thing, because 16 input is there and 32 output combination are there. So some of the output combination are not used because 16 only will be utilized. 16 will be free to us. So we can use this 16 for other use. We can use these non-data codes to represent the physical layer control signals. For example, in these 2 columns, you see there is node 1, 1, 1, 1, 1. You will not also see 1, 1, 0, 0, 0. So we can use this as idle line and the other one as the start of a frame. There is another alternative approach in order to make the data look random. We don't want a series of zeros, series of ones. So here we have scrambling. For example, scrambled egg you eat and you don't know which part has gone where. So this scrambler, how does it work? This works by XORing, that is using the XOR operation. So XORing data with the pseudo-random sequence before transmission. Random is just, if you say random 10 numbers, so sometime 1 can come, 10 can come, 9 can come. Pseudo-random is random number will come, but there will be some statistical or background thought. so that data will be XORed, okay, before transmission. And receiver will again at the receiver end will XOR the incoming bits with the same pseudo random sequence which was taken by the sender in order to recover the real data. So scrambling is quite attractive because it adds no bandwidth and there is no time overhead as well. One more thing in scrambling is it helps. Why? Because random signals tend to be wide. What does it mean wide? That is, these signals have energy, they are spread across the frequency components. Okay, that is why we are calling it as wide. But if the data are the same as the pseudo-random sequence, data and pseudo-random sequence are same, XOR operation will give you all zeros. This also we have to see. This has happened. Earlier version of the standards for sending these IP packets over SONET links in the telephone system had this defect. Balance signals. This we'll discuss in the later discussion. Thank you so much.